Cosmologists can trace the evolution of our universe back 13.8 billion years to the Big Bang. But the Big Bang itself is an event still shrouded in mystery. In this series, we explore competing models of the early universe. While cosmologists may disagree as to the true nature of the Big Bang, what they do tend to agree on is that when the entire observable universe is far smaller than an atom, the strange world of quantum mechanics surely becomes relevant. At Cambridge University, one of the first attempts to build a cosmology based on quantum theory was pioneered by Stephen Hawking, Thomas Hertog, and James Hartle. Their theory is known as the no-boundary proposal. In this episode, they'll explain how their no-boundary proposal may be able to tackle some of the deepest mysteries of our existence. From why is there an arrow of time? Or is there a multiverse? And how do we resolve the Big Bang singularity itself?
Roger Penrose and I showed on theoretical grounds that if Einstein's general theory of relativity is correct, there must have been a singularity in the past, a point of infinite density and space-time curvature, where time has a beginning. However, although our singularity theorem predicted that the universe had a beginning, it didn't say how it had begun.
The singularity theorems, Penrose, Hawking, and others, showed gravity would become so strong in the beginning that the classical physics would break down. That meant that quantum physics was inevitably going to be important.
The idea to use quantum cosmology to understand the origin of the universe goes back way before Penrose and Hawking. In fact, it came along with the discovery of the expansion of the universe. So even in the 30s, people began to ask the question, well, what happens at the origin of the universe? And the suggestion was made back in the 30s that at the very early phase of cosmology, in the very early phase of cosmological evolution, quantum theory would come into play. But of course, in the 30s, the tools were not available to say anything about the origin. This was just an idea for an idea, as John Wheeler would have said.
The initial singularity theorems developed in the 1920s by Friedman and Lemaitre had the unreasonable assumption that the universe was perfectly symmetrical. In the 1960s, Penrose and Hawking developed new singularity theorems that did not require this premise.
So in the early days, you could have said, well, the initial singularity, the initial Big Bang singularity, is a feature of very specific universes. But Penrose and Hawking showed that, in fact, this initial Big Bang singularity is a generic feature.
The real lesson of the singularity theorems is therefore that we need to combine the general theory of relativity with quantum theory in order to understand the origin of the universe.
In the 1970s, Stephen Hawking discovered that when quantum theory is applied to black holes, it causes them to evaporate, giving off what is now known as Hawking radiation.
Stephen and Jim both realized that if quantum theory has such a big effect on the singularity inside black holes, presumably it also has something to say about the cosmological singularity.
It was at a conference in the Vatican in 1981 that I first put forward the suggestion that maybe time and space together formed a surface that was finite in size but did not have any boundary or edge. Together with James Hartle from the University of California, I worked out what physical conditions the early universe must satisfy if spacetime had no boundary in the past. Our model became known as the no-boundary proposal. It says that when we go back towards the beginning of our universe, space and time become fuzzy and cap off, somewhat like the North Pole on the surface of the Earth.
In the singularity, the Big Bang is a moment of infinite density and curvature. But in the no-boundary state, there's a smooth surface, which, although finite, does not have a single point of origin.
The key concept is the idea of a wave function, that sometimes a particle can act sometimes like a wave and sometimes like a particle, a photon say, right? When it's acting like a wave, it's described by a wave function.
The no-boundary proposal treats the universe quantum mechanically, and therefore the mathematics needed to describe this strange quantum world will be needed for the universe as a whole.
And the starting point to do this is Richard Feynman's sum over histories formulation of quantum theory. So unlike the Copenhagen interpretation of quantum theory, where you have an external classical world, in Feynman's sum over histories formulation, everything is part of the system. It says essentially that if a particle goes from A to B, it doesn't follow a single history, but it follows all possible paths connecting A to B. Just like in the famous two-slit experiment of quantum theory, where you have a particle that goes through both slits, and the superposition of paths.
A path integral assigns a weighting, or relative probabilities, to different possible histories of the universe. The no-boundary proposal is a selection principle that selects the subset of histories of the universe that close off in the past, and so allows us to determine which histories of the universe have the most significant contribution.
The most significant contribution will come from a geometry that is Euclidean on the bottom of the shuttlecock and an expanding de Sitter universe on the top of the shuttlecock. What I mean when I say the geometry is Euclidean is that it has 4 space dimensions and no time dimensions. What I mean when I say that the geometry is Lorentzian is it has 3 space dimensions and 1 time dimension, just like the geometry we experience every day in this room.
The no-boundary proposal is a model of the Big Bang that is based on quantum gravity. It is given by the path integral over all Euclidean metrics without boundary. By contrast, the Hawking-Penrose theorems are about Lorentzian spacetime, which has a boundary at the singularity.
To describe the wave function and its superposition, physicists use imaginary numbers. But what are these imaginary numbers, and why are they so important for the no-boundary proposal?
Well, imaginary numbers are numbers which square to something negative. I is an example, and I squared is -1. The no-boundary wave function describes or assigns different probabilities to different histories of the universe. And it does so by associating each history to a geometric construction, the famous shuttlecock construction, in which a history is in fact rounded off in imaginary time. In this context, when we say imaginary time, the no-boundary proposal, we are really talking about geometries in which time behaves as a space direction. The no-boundary proposal does not describe a single history for the universe, but it describes an ensemble of different histories.
The past is probabilistic, just like the future. It's symmetric.
So in that sense, it is similar to a wave function of an ordinary quantum mechanical system, which describes an ensemble of different histories or paths, just like in the two-slit experiment.
So if that's true, then there must be a wave function for the universe. And the question is, what is it?
So this is the formula for the no-boundary wave function. What does this mean? The no-boundary wave function the no-boundary wave function gives you an amplitude, a weighting for different configurations at some moment of time, different kinds of universes. You could think of each h and phi as a universe. The amplitude of each universe, according to the no-boundary wave function, is given by a Euclidean path integral. There is no notion of time at this level. Time does not appear in this formula. Now there's a special condition, the no-boundary condition, which asserts that those histories contribute to the path integral which have no other boundary except the one at which you're evaluating the wave function. And that's what leads to that shuttlecock picture. How am I going to draw a geometry which has no other boundary than the boundary at which I'm evaluating the wave function? I naturally draw something like this, right?
So these shuttlecock geometries, they are geometries, complex geometries, which start out with all dimensions behaving as a space dimension.
This region, which is Euclidean, and where all dimensions behave as a space, changes. The spatial dimension remains a circle, but the time dimension opens up and becomes distinct from the space dimension and describes a universe in which a spatial circle grows and grows and grows. I can no longer interchange time and space here. This is the way time, Lorentzian time evolution, emerges when the universe gets larger from what is initially a quantum fuzz.
Classical physics is not fundamental. It's an emergent phenomenon, we believe, from a quantum mechanical theory.
The notion of classical evolution emerges from the no-boundary wave function when the universe gets sufficiently large. According to the no-boundary proposal, the only way to get a classical universe with a deterministic notion of time is via a period of inflation.
Inflation is a period of incredibly rapid cosmic expansion believed to have occurred in the early universe. Inflation is thought to solve a number of problems with standard Big Bang cosmology, and it's driven by a form of matter known as a false vacuum, which causes the expansion to accelerate instead of slowing it down. When this form of matter decays, inflation ends, creating a hot soup of particles.